On everybody. Today we're doing another LeetCode problem. Today we have a LeetCode medium. This one's called 2sum2, so it's basically like 2sum except the input array is sorted. So I'm going to be solving this in C++. So yeah, let's get into the solution. So we're given a one indexed array of integers numbers. So really what that means is it's a regular array. They just want us to return our indices, like adding one to them, which is interesting, but we can do that, no problem. So given a one indexed array of integers numbers that's already sorted in non-decreasing order, so imaginably that means increasing order, non-decreasing. It's kind of funny to me, but find two numbers such that they add up to a specific target number. Let these two numbers be numbers index 1 and numbers index 2, where those indices are going to be in the range of 1 and then the size of the numbers array. So this is just like 2sum. We're just looking for two elements in numbers that add up to target, and then the only difference is they want us to return those indices as being one indexed. The other important thing here is they want our solution to use constant extra space. Now, if you've done 2sum and you are familiar with that problem, it's like if the array isn't sorted, like there's no way to get to linear time without using linear space. But the array here is sorted, so we actually can get a linear time algorithm, being that the array is sorted without using using constant extra space. So the key here is going to be using 2 pointers. So for the optimal approach for this problem, we're going to be keeping in mind the array is sorted. Keeping in mind the array is sorted, use 2 pointers. It's going to be a left and a right pointer, and we're going to inch them along until we find those two elements that add up to the target. So for this problem, the time complexity is going to be big O of n, and then the space complexity for our solution is going to be constant, because we're not going to use any additional data structures, just the 2 pointers. So for the algorithm, we're going to have a left pointer, and we're going to set that to 0. We're also going to have a right pointer, which is just going to be at the very end, like the last index of numbers. So to get that, we just do numbers.size -1. And then basically, we're going to want to inch these pointers towards each other, so incrementally. So we can do this while r is greater than L. Now, this is really just for safety. It says that the tests are generated such that there's exactly one solution always. So if it got to this point, we would like pretty much be at the solution, since it's like guaranteed to exist. But anyways, just like an observation there. So while r is greater than L, we're basically going to have a current target. So I'll just say in current target, or current, because there's the desired target, right, that's given to us. And I honestly don't like that variable name, current target. Maybe we'll call it current sum, because it's really just the sum of the two elements we're currently looking at. So and then obviously to get the current sum, we have our 2 pointers, we have numbers, so we just need to index into numbers like this, so with both of the pointers. So numbers L plus numbers R, and that gives us the current sum. And then basically we want to check It's like, so we need to think about what we're gonna do. Like, well, first of all, there's the case where we have found the target. So so we can get that out of the way right away here. So if the current sum is equal to the target, we can just return true, or not true, sorry. We need to return a, let's see, a vector of those integers for those indices. So we can, let's see, I'll go ahead and declare a vector of integers here for the result. So vector int, we'll call it res. We'll make it size, allocate that size right off the bat. And then, so if the current sum is equal to the target, then we can set res at 0 equals to the left index plus 1. And then similarly, we add 1 to the right index, and then that's the solution. We just return res. So that's once we found the target. So if we haven't found the target, we need to think about, how to move the pointers based on the current sum's relation to the target sum. So if the current sum is less than the target, it's like, how do we make the current sum greater so that we can get closer to finding the target? Well, to make the current sum greater, you would increment the left pointer, because as you can imagine, in like a sorted array of integers, if you're moving the left, if you're increasing the left pointer, your sum is going to increase because you're going from a smaller number to a greater number. Likewise, if your current sum is greater than the target, and you want to increase the current or decrease the current sum, then you would move the right pointer down. That way your sum shrinks and gets closer to the target. So the code for that is just, if our current sum, we just literally compare it to the target. So if the current sum is less than the target, then, or greater than the target, sorry, if the current sum is greater than the target, we want to shrink the current sum, so we decrement the right pointer. And then the other scenario is where the current sum is less than the target, in which case we increment the left pointer to increase it, so to get closer to the target. So you pretty much just keep doing that, and then the nature of this algorithm is such that and obviously the test cases are guaranteed to have exactly one solution, but the nature of all of that is such that you're eventually going to find the target. So yeah, so that's pretty much it for this problem. I think I probably still have to, C++ is going to demand that I return something down here also, because you have to return something in all control paths. I'll just set this to -1. Like, you're always going to find a solution. So like for this particular problem, because that's what it says. So like you wouldn't really ever get here, but C++ demands you return something in all control paths, so we have to do that. But I'll run this code so we can see if there are any bugs. Doesn't look like it. And then submit, just so we can get our percentages. So it beats 37% for runtime, beats 60% for space. This is the optimal solution. So I'm sure there's optimizations you can make here to get the runtime better for C++, but nevertheless the time complexity here is as good as it gets. So hope you guys enjoyed this video. Hopefully it helps you. If you want more of these, as always, like and subscribe, and I'll see you guys in the next.